Okay, so maybe we're ready to start. So thank you everyone for coming, and welcome to this third instance of the Cardamom Seminar Series. So this series is sponsored by the Cardamom Project, which is an Irish Research Council funded project looking at models of natural language processing and word embeddings for minority and historical languages. So I'm very happy to have Remo Nitschke here. He's a PhD student at the University of Arizona, looking into areas of syntax and NLP for low resource language. He's going to talk today a little bit about the application of neural machine translation, particularly looking at Romance languages and the Uto-Aztecan language family. It sounds very interesting. So yeah, Remo, when you're ready.
Right. Thank you, John. Let me go ahead and share my screen. Let me see if I can get this into. All right. Can you see the slides, or do I need to?
Yeah, we see your slides.
Perfectly.
So
all right. Thank you. So yeah, thank you, and welcome to my talk. So as John already pointed out, I'm going to talk a little bit about neural machine translation, but in the context of a vocabulary reconstruction task. And the two applications I'm going to talk about involve the Romance language family and the Uto-Aztecan language family. So all of this is really kind of work in progress right now. So I definitely welcome any comments and ideas, and any other comments on how to improve any of this. All right. So outline of the talk. I'm going to do a very short sort of talk about machine learning and low resource languages, but I assume I'm going to be preaching to the choir here, but it's always good to establish some kind of baseline. And then I'm going to talk a little bit about language revitalization and how the comparative method is used in some contexts, at least in the Americas right now, which kind of formed the initial impetus for this project. And then I'll talk about my recent work, which is also a paper, which is called Restoring the Sister Using Neural Machine Translation to Reconstruct a Vocabulary from Sister Languages, or something like that. It's in the references at the end of the slides. Well, I'll talk a little bit about that project, which was essentially a proof of concept of this whole idea. And then if there's time, I'll go a little bit into the Uto-Aztecan work, which reminds me, I'm going to set a timer so we have some time for discussions. All right. Okay, so the first part, again, going to be preaching to the choir, so I'll try to make it quick. But I think we can all agree that machine learning-based NLP has made some pretty good progress in the past decade. But most of this progress has been focusing on what I'm going to call majority languages, right? And just for myself, I would define majority languages here as either politically or financially dominant languages in terms of the communities that they're spoken by. And since much of modern NLP is driven by industry, right, the financial aspect is a huge drive. But obviously the other part is these languages tend to have the most data available. And since much of modern NLP is neural net based, a lot of data is good and not a lot of data is very bad, right? So that's also how we get this diversion. So minority and low resource languages have been largely left behind in modern NLP, although there's been some efforts lately, right, to rectify this, the Cardamom project, I think, being one of them. But as I said, since we're using a lot of neural nets, we need large data sets to be effective. All right, so much for preaching to the choir. I want to distinguish between a couple of kinds of low resource situations, and the slide says two kinds of low resource, which is wrong. And this is just for myself essentially, but I'm focusing on one very specific kind of low resource situation, which is why I'm making this distinction. So the first kind of situation is essentially the language has a speaker community, the data is sparse, but it can still be collected, right? And the reason why it's a low resource language is essentially because nobody has bothered to collect the data. So these are situations we find all around the world, essentially. Then there's another situation where it's a little bit more dire and the language has a few surviving speakers, right? But there's no sort of larger speaker community where language is passed on to the next generation, right? There may be revitalization efforts in progress, the data is sparse, but it can technically still be collected, right? As long as we have speakers, we can technically still collect data, right? But obviously, as we have fewer and fewer speakers of these kinds of languages, the less opportunities we have to collect data. And these kinds of situations are fairly common, at least in the Americas. And then the third one, which is the one I want to focus on for this project, is the language is dormant or inactive and is ideally undergoing a reclamation or revitalization effort. What this means is there are no native speakers of the language currently alive, but sort of to distinguish between an extinct language and an inactive or dormant language, an inactive language is not spoken anymore, but there's a community still around that is somehow culturally attached to it or through their identity attached to it, right? So the language is not around anymore in the sense that there's no L1 speakers, but the community still exists. And hence there's usually also a drive to preserve or reclaim the language. This is different from a case like, Gothic or something, where the speaker community or the descendants of the speaker community also don't exist anymore, where the language is sort of truly extinct. But these cases have the problem that you can no longer collect data, right? Because we have no L1 speakers anymore. And these latter two situations are situations we often find in the Americas. And there are, of course, big speaker communities that fall more under the first bullet point, such as the Navajo speaker community or Nahuatl or Quechua. But 2 and 3 are really common in the Americas as well. And 3 especially is, of course, a big problem, especially for those communities, right? So in this third case of a dormant language that's undergoing a revitalization or reclamation effort, the available data can really limit this kind of effort, right? If we have no remaining speakers, the community has to rely on the historical data that has been recorded. And in a lot of those cases, that's data that was recorded 200 years ago, often by missionaries who didn't use any standardized way of spelling. They didn't have an IPA, right? So there's all kinds of problems that are involved there. And sometimes some of these communities are left with very small remaining lexica of lexical items that their languages have, right? So to get around this problem, some communities have started to use the comparative method, like the historical comparative method, in order to recover lost vocabulary pronunciations. And there's a project within the Algonquian language family that does this, where they essentially use a style of historical comparative restoration, but instead of restoring a protoform, they're restoring essentially a sister form, right? And the reason they're doing this is because some of those lexica are just too small and they need to find what the entry would have been, essentially. So here's an example, right? This is from Delgado et al. This is Algonquian. This just illustrates the historical comparative method. I don't think I need to introduce it much, but essentially you have here a cognate set of the term for fish, right? And in the middle is our target pattern, what we would like to know, but we don't know what the target is. So by looking at a lot of these sets, right, we can sort of reverse engineer what the different morphological and phonological developments of the languages were, and then we can make an educated guess of what the term for fish would have been in our target language, right? That's essentially what people are doing right now in a few select cases where there really is very little of a lexicon left. Of course, the sort of requirement for this is that you have sister languages which are well enough documented for you to even find these cognate sets in the first place, right? So that's another issue that's at play here. So right now, this work is done manually, basically by the community and associated linguists. But essentially, you can understand this as a type of sequence prediction task, right? You feed in a couple of sequences, which are the cognates from your sister languages. and your target sequence is the cognate in the language you're looking at. So if it's a sequence prediction task, maybe we can train a model, specifically a neural machine translation model, to do this kind of task for us instead. So instead of having to do it manually, perhaps we can at least automate that process, right? A huge problem here, of course, is the size of these data sets, right? For example, Opata, which is a Uto-Aztecan language, which is currently undergoing a revitalization effort, their current online dictionary has 433 entries, right? 433 entries is not really a data set of the size where you're going to think about doing anything neural net based, right? They have some older historical dictionaries as well, which are a little bit larger, but not by much. All right, so this is essentially the backdrop to the talk, to sort of have the situation at hand explained. Now, this was essentially the impetus for the project itself. The idea of saying, okay, maybe we can automate this process. Maybe we can train a model to do this for us, right? But we need some way to get around this data sparsity, right? Because we can't work with 450 entries. So now comes the part where I talk about the paper, essentially. So I did a proof of concept of this idea within the Romans family, which is a paper you can look up the references at the end of the slides. And essentially, I was trying to, first of all, determine if this is at all feasible in the first place. And then the other main aim of the project was to see how can we compensate for this lack of data. And the idea was the way we compensate for the lack of data is by using multiple parallel input languages, right? So to go back to this earlier slide, instead of going from namas here to the target or names here to the target, we try to use all of these at once in some way. This was sort of the basic idea. And fortunately, somebody already did a similar idea, essentially. So Meloni et al. 2019, they essentially did something very similar, although they weren't looking to reconstruct for any revitalization purposes. They were essentially just trying to see if they can predict Latin protoforms from Romance cognates, right? So they had a large cognate set of the Romance languages, and they trained a neural machine translation model to reconstruct Latin predecessor forms. And the model achieved a fairly okay accuracy for the amount of data it had, with 84% within an edit distance of 1, right? So 84% of the testing output was either already on the gold standard or within 1 edit of the gold standard. And they were kind enough to make a subset of the data available to me for my proof of concept. This looks terrible in the full screen. I didn't realize it was going to be this pixelated. This is just a picture of what the data set looked like as it came to me. It's just a text file. Every line is essentially a set of cognates, and the languages are separated by a tab. So you can see you have all the Latin forms on the outer edge, and then in between you have the Romance forms. And as you can see, there are gaps in the pattern as well. So they were reconstructing Latin forms from modern Romance forms, right? Which wasn't really the task I was interested in. So I wanted to reconstruct essentially modern forms from modern forms, because the aim of the project was to aid in a revitalization project. So you needed to be able to have a target language and a couple of sister languages and work from the sister languages to the target language, right? So I had to tweak the data in some ways. So I had to remove Latin from the set because it wasn't interesting for this project. And I had to find the language with the most cognate forms in the set, which turned out to be Italian, because essentially I wanted to have a target where I had the most amount of data to play with. And then I had to remove all lines which did not contain the Italian form and all lines which contain only an Italian form, right? So to give you an example here, for example, line 1, that's something I would have had to remove because there's no Italian target, and I need, for the training data at least, I need something to train towards. And then line number 3, that's also something you have to remove, obviously, because you can't train the model on 0 input, right? All right. So after tweaking all this data in the set, this left me with 3,527 cognate sets. And a lot of these are sets where some patterns are empty, right? There are only very few where you have a full set where every language has a corresponding cognate. Now I split these up into 2,466 lines of training data and then validation and testing. Now 2,466 is still very pitiful for anything neural net based, right? Especially for any state-of-the-art neural machine translation system. But the idea was by having this sort of parallel input, we would be able to compensate that to some degree. All right. So if we train a model, we have to think of how do we feed it the input, right? And since we're training from multiple cognates of the sister languages, right? So that was Romanian, Portuguese, Spanish, and French. Since we're training from the sister languages to the target language, we have to find a way of how we feed the input, right? And there would be 2 obvious solutions. One would be a serial configuration, where we essentially feed one cognate and then have the target be the corresponding cognate, and then we feed the next cognate, have the target be the corresponding cognate again. So essentially, for example, you could have every input line as a cognate from one language, and then for those 4 input lines, you average the output in some way, right? But that gives you a huge problem because there are a lot of empty patterns, right? So the serial configuration didn't seem like a good way to go. So instead, I used the parallel configuration, which is what Meloni et al. Used as well, which essentially means each input line contains all the forms we have for that target cognate, right? So if you have Mosto here, the input line is going to contain all 4 of these, right? And I concatenated these by sort of concatenating them character by character as opposed to word by word, right? So these four forms, you could just concatenate them word by word. Instead, I sort of created this Frankenstein type of representation, which seemed to work marginally better, at least in testing, than just doing it word by word. All right, so this is the input setting. Since I talk about parallel input here a lot, I just want to really quickly define what I mean by that. Since a vital aim of the experiment was to investigate how far we can sort of compensate lack of data by augmenting the information in the input, and this is because of the intended use case, right, a language revitalization context. So if you assume language X, which is undergoing some type of revitalization or reclamation effort, and we have a lexicon of language X, which has approximately 2,000 lexical items, right? And let's say we're really lucky, and of those 2,000 items, 1,000 are cognates with known sister languages that we have records of. And this is already very optimistic. Then those 1,000 cognates essentially form the hard upper limit of the amount of training data lines we can really acquire, since we can only train our model towards attested forms of the language, right? We could envision a case where we're a bit adventurous and we just invent forms that we think the target should be, but that I suspect will get you into a whole other host of problems. So really, the size of the lexicon of the language you're given, that limits the amount of data you can train your model on, right? So you need to find other ways to augment this data, because obviously neural nets need large amounts of data, and we need some way to get that information in there. So the idea is perhaps we can compensate this by adding more information into the input line, as opposed to just increasing the amount of input lines, which is a way that's not really available to us because we have a fixed amount of training targets, right? So instead of training from language Y to language X, we're training from language W, Z, Q, T to X. And we're sort of mashing all that input together in order to augment the amount of information that's in an input line. And we're just hoping that the empty patterns, that the network can just deal with it, right? Because there'll be tons of empty patterns as well. So lines where only 3 of the input languages will have a cognate, or only 2, or only 1. And we're just hoping that the model will be able to deal with that. And it turns out it mostly is able to deal with that. All right. Let me just quickly check my time before I go on. There we go. Okay, perfect. All right, so what was the experimental setup? Oh, right, one thing, since Cardamom is also about embeddings and things like that. Essentially, normal neural machine translation models, right, do a sentence-to-sentence translation, right? Now, for this type of task, you don't want a sentence-to-sentence level translation. You want a word-to-word translation. So essentially, you feed the model characters as if they were words, basically. So if you're thinking about a normal neural machine translation framework, instead of having a word level encoding, you have a character level encoding. And for this project, I didn't use any custom embeddings. The embeddings were done by OpenNMT, just as an aside. All right, so this proof of concept was run using the OpenNMT Pi framework in a no configuration setup. Okay, so it's just the basic they had in the version I was using, which was for that one a 2-layer LSTM, 500 hidden units on encoder and decoder. The no configuration setup has sort of 2 basic reasons. First of all, I just wanted to see how tweaking the input will change it as opposed to the hyperparameters. And the other reason was also, this was a while ago and I was sort of also learning neural machine translation. So I didn't want to mess anything up by tweaking the wrong hyperparameters. So that's also the other reason. All right, so for this, I trained multiple models, all right? So starting out with a baseline model, which was the full-size data set, so all 2,466 input lines and all 4 input languages. And then I trained 2 sort of other types of models. One series of models where I kept all the 4 languages, but I reduced the amount of input successively. So reducing the input by 10%, reducing the training input, obviously the training data by 30%, training data by 50% and by 70%, right? And then on the other hand, I ran a series of models where I reduced the amount of languages that I was feeding into the training data. So take 1 language away, take 2 languages away, take 3 languages away. And the idea was to compare how these 2 approaches would shape up, and hopefully showing us that by adding more languages, we essentially get a similar effect as by adding more input lines, right? Which would tell us that if we add more languages, we can get away with fewer input lines, which means the more languages we have, the smaller of a lexicon we need as a baseline, which is very good, right? As a basic concept for this type of use case, where our lexicon is always going to be limited. All right. As I said, this was done in order to compare how these 2 approaches shape up, with the hope that reducing input lines is comparable to taking languages out of the equation. All right. And this is the results. This score you see here on the side is a custom score I devised for this project. Essentially, it weighs edit distance. So it essentially, anything that goes beyond an edit distance of 4, it weighs as useless. And if you have an edit distance of 0, you get 1 point. If you have an edit distance of 1, you get 0.9 points. And then you average it all out. So the best score you can potentially get is 1. That would mean all your test data is right on the gold standard, right? So what you can see here, this first line, that's the baseline model. That's all 4 languages with the full amount of training data. So you can see 44.63% within 0 edits. So that's the amount that was right on the gold standard. which, you know, if it's a neural machine translation task, that's sort of pitiful. But considering the use case that we have here, I don't think it's all too terrible. Because if this is a type of revitalization context, right, where a community is trying to expand the lexicon, and you run this type of model, then essentially whatever comes out of the model is really just a suggestion for the language community, and the output would also be vetted by somebody familiar with the language. So if there's small edit errors, right, and these are things like you have a double T instead of a single T and things like that. If there's those small errors, those are things somebody vetting the output can control for, sort of as a human intervention. And then obviously the community would have to make, the language community would have to make some type of decision as to whether they want this lexical item in the language or not, right? Because the model just gives you a prediction or a suggestion. So in terms of score, the baseline model, as you would expect, performs the best as well. And the score is really just a reflection of how the edit distances are measured. But essentially, the more you have outside of the 4 edit distance margin, the worse your score is. And the idea behind that was, if you go beyond an edit distance of 4, you're essentially useless to a language revitalization effort, because the prediction is so out of whack that you can't fix it anymore by looking at it. That was the idea behind this. All right. So let's talk a little bit about these numbers. As you can see, these are basically the cases where I took away the languages successively, and these are the cases where I reduced the input. And this is all the time window at 10,000 training steps, essentially. But these things, they plateau pretty early. They plateau around 5,000 steps in OpenNMT at least. And as you can see, as we would predict, essentially, taking away languages gives you worse performance, and taking away input line gives you worse performance. But how does it shape up in relation? And for that, I want to look at the sequence over time as well, because these models aren't super stable. So this is essentially the score over time or over training steps. So starting here at 0 and going up here to 10,000. And this was measured every, I think, every 1,000 steps. You can see they're not super stable. They fluctuate a lot over here in terms of the score, which probably has to do with the little amount of training data they're getting. And there's something interesting happening here, which is the blue line, which is the baseline model, and the orange line, which is essentially the baseline model minus Romanian. They seem to sort of be at the same level until the 10,000 steps where they diverge, but that's just a random diversion. What's interesting here is it seems that taking away Romanian didn't really have a significant impact as opposed to taking away another language. So here, looking at the red line, that's the that's Spanish, Portuguese, and Romanian. So instead of taking away Romanian, I took away French, and that has a real drop-off. So I think what's going on here is that Romanian was the language that had the fewest amounts of forms in the data set. So it may be the case that essentially below a certain threshold, Romanian is confusing the model really about the same amount as it's giving it additional data. So we can't just sort of wildly add languages to the mix. They really have to have a significant amount of cognates with the target. So it probably doesn't pay off if you have, say, 1,000 target cognates. It doesn't pay off to throw in a language that has like 200 corresponding forms. That's just not enough. So I think that's the reason why that's happening here. The other thing also is Romanian, at least in terms of sort of what historical linguists think, is assumed to be the most distant of these four, of these 5 languages within the Roman set. So the first takeaway here right away is you can't just add languages willy-nilly. There really has to be a certain amount of cognates with the target forms. Basically, that's sort of the first takeaway we have here. And that's also, unfortunately, a reason why the results of this are kind of skewed, because Romanian is in the mix. And while I was writing this paper, I was a little bit under stress and I didn't check all the possible combinations. So there might be stuff here still that I'm missing. All right, now let's compare that to the case of reducing the amount of input, right? What we're seeing here is taking away languages. And also, as you can see, if you only have one language, that's purple, by the way, you perform rather poorly, right? So we can really see that adding extra languages, it really does make a difference. And Spanish, by the way, was the language that had the most corresponding forms with Italian. So anyway, all right. How does this shape up to just taking away input lines? This might look a bit confusing because there's a lot of lines going on. I hope you can parse the color. So blue here is our baseline model, right? All languages, full amount of training data. Gray is taking away 10% of the training data input. So that doesn't seem to have terribly much of an effect. Then black over here, that's reducing it by 30%, whereas red over here is taking away French. So that's good. That seems to hint that at least with this data set, it seems to be sort of equivalent of a 20% input reduction of just taking away a language, right? At least up here. It gets a little bit muddier the further you go down, unfortunately. So the brown line, that's reducing the input by 50%. And that's still performing better than the case of having only Spanish, that's good. And then if you reduce it by 70%, it's just garbage, unfortunately. So that was around, I think, 900 input lines, right? Now, if you think back to Opata, which I discussed earlier, which has around 450 current lexical entries, that doesn't really paint a pretty picture for the intended use case here, right? If you're already getting this terrible performance at a reduction of 70%, which was around 900 training data lines, if you're starting with 450 something, you'll probably get terrible results. And we'll see this as we get to Uto-Aztecan, unfortunately. All right, so what's the outcome of this first paper? Well, first of all, we can see that we can use a neural machine translation framework to predict cognates of a target language from cognates of its sister languages. So that's good, right? We can also see that we can augment the input lines by adding sister languages to the mix. And this will at least supplement or compensate the lack of data that we have in a given context. So that's also good. As demonstrated with Romanian here, it doesn't look like we can just blindly add languages, right? So I guess that's not so good. Another thing is we don't know how well this works with different types of morphology, right? Romance languages, all right, very well researched language family, and you know, they're not like agglutinative or anything like that. So we don't know how this shapes up with, say, a polysynthetic language or something like that, which is a lot of the cases that we have in the Americas, which is kind of the intended use case, right? So that's not good. But at least we know for Romance it works, sort of. And here's another big caveat, which is you can only reconstruct cognates through the system, right? Because you're training from cognates to cognates. And there's really no good way to train from unrelated words to other unrelated words. That's just not going to go over well. But no language is just cognates, right? Really, cognates are usually a fairly small subset of most languages. And that's another issue, and that's something that anyone who would like to use this type of approach has to be very conscious of, right? The model just gives you what it thinks a cognate in your language would be. But in a lot of cases, you might not want a cognate, right? And then finally, the amount of data needed for this approach is still too large for a real-life application in the intended use case, right? As we saw earlier, once you drop sort of below 1,000 lines, you get major drop-offs in performance, and it starts to be pretty terrible, unfortunately. All right, so this is the paper that's already out there. So now you don't have to go read it. So let's move on to the work that I'm doing right now, or I'm trying to do right now. And this one is really work in progress. So I'm happy for any comments and ideas. So I'm currently working on a cognate set of the Uto-Aztecan family, which I graciously received from Kenneth Hill as an RTF file, and I turned it into a machine-readable parallel cognate corpus in the style that I received from Meloni et al., which took a little bit of a while because I got an RTF file in the beginning and it needed a lot of regexing to get this thing going. But now I have it, and I'm also happy to share it, and I have permission from Kenneth Hill to share it. So if anyone's interested in the set because you want to do something with Uto-Aztecan, send me an email. Right now it contains 1,357 cognate sets of the Uto-Aztecan languages, which sounds like a lot, but unfortunately the Uto-Aztecan family, it's very big, and some of the languages are fairly distant with each other. So it turns out only very few languages even have more than 300 forms in the entire set. So while we have 1,357 cognates in the whole thing, for most of the languages, we barely hit 300 or more, right? So that's not good. The Pima Bajo language, which is a Southern Uto-Aztecan language, is right now the language with the most forms in the data set. And that one has 441 cognates in the set. So this is like about the size of the entire Opata dictionary, right? And this is the largest sample I have right now in the set. And unless I find any other cognate sets out there, that's as much as I have for Uto-Aztecan. So that's the baseline I have to work with, which is not good because Pima Bajo is not even a language where you would need this type of thing. You would need it with Opata, but with Opata, you even have fewer cognates in the set, right? So that's quite bad. So in order to test the proof of concept with an indigenous language that's actually to a degree endangered and might undergo a revitalization project at some point, I selected as Pima Bajo as a sort of testing target, essentially. And I looked for all languages in the corpus that share 200 or more cognates with Pima Bajo in order to avoid a case like Romanian, that we had earlier, where we saw that adding or removing the language didn't really make a difference, probably because it just didn't have enough cognates available, right? So the languages in the set that we have that meet this threshold are Tono Odham, which is spoken right around where I currently work at the University of Arizona, so that's great. Northern Tepuan, Southern Tepuan, Guarihio, and Raramuri, and all of those are Southern Uto-Aztecan languages. And I split this into 314 lines for training, which is just extraordinarily pitiful. 39 lines for validation, 42 for testing, which means even sort of with the output of this experiment, it's even hard to tell because we have so few testing lines that it's not even statistically significant, right? As you would predict, this performed very poorly, achieving a custom score of 0.48. So to go back to the initial results, right, the lowest score achieved here was 0.59, which was the 70% reduced input. And that's already, pretty terrible. 17% within 0 edits, 26% within one, and then it gets sort of better at the 2 edit margin. It's even worse for Pima Bajo, unfortunately. So there are no forms that meet the gold standard, okay? 0 forms in the testing data that are on the gold standard, and 10 forms that are within 1 edit. But also, a lot of these cognates are a little bit smaller in terms of character length than the Roman set. So you kind of have the impression that 1 edit here is worse than 1 edit in the Roman set, right? Anyway, so with this current version, unfortunately, we're not looking very good, at least with the neural machine translation approach. So to get to my sort of final comments before I open this up for discussion, it seems fairly clear that the 441 forms are just not enough. However, right, this is all no configuration approach. I'm playing around with hyperparameters a little bit more right now, but perhaps, you know, the no configuration approach is really killing us here because of the size of the data set. So I welcome any ideas, different type of model, smaller models, you know, different configurations that might give us a little bit better performance, because right now it's not good. Another thing is, you know, perhaps having this low resource situation, we would be better served with a rule-based or finite state approach, right? A lot of people working with low resource languages, you know, usually do some finite state morphology type stuff that, you know, I at this point don't fully understand, but I'm looking into it. And I can imagine that with this little amount of data, you might actually be better off using that. So that's sort of what I'm looking at right now for the future, because I don't think with this small of a data set, the neural approach really has a lot of things to offer. But, you know, there are potentials for improvement. You could try and do different types of embeddings. Right now, this is just a character level embedding, and you let OpenNMT do it. Perhaps you can find an interesting way to do pre-trained embeddings. Perhaps Viper encoding might be better here. I can't really tell. Perhaps there are some different ways to treat the input, but these are things I'm still sort of thinking about and hoping perhaps some of you have interesting ideas. Yeah, all of this is work in progress, so I welcome any ideas, and yeah, thank you. I'm opening it up for discussion and questions.
Okay, thanks. That's really interesting. Yeah, it seems like it's much harder to take these approaches, and you know, we have so few examples. So maybe I'll ask if there's some questions or some comments from the audience.
I'd ask a question if that's all right.
Go ahead, Adrian. Yeah.
Thanks. Firstly, thanks very much. It's great to see this kind of research being done, and I'm glad to know that I did something similar with LSTMs. I'm glad to know that I wasn't completely out of kilter looking into this this area. Maybe something that would be of interest to you is looking at transformers rather than LSTM. They're meant to be better. Although what I would say with a data set like this, I've come to think, based on the size of it, as long as there's a certain standard of spelling and such in the target language, maybe you'd be better looking at a rule-based approach, like and Doris can chip in here because he knows a lot more about finite state transducers than I do, but I think that would be the perfect fit for a job like this. My question is related to your model itself, actually. You had a slide up before you showed us the results where it said, I think you had 500 nodes per hidden layer, and you had 2 hidden layers.
Yeah, that was just the no configuration setup for OpenNMT Pi, basically. Yeah.
Okay. And do you know what size the input layer was? I mean, was it much smaller or bigger than that?
I don't know at the top of my head. No, I don't know. I would have to
Okay.
run it again and look at the log.
The only reason I say it is because I had massive issues with overfitting when I started to approach the number of hidden layer nodes that I had nodes in my input layer. And I suspect that you might be able to get some more performance out of the model if you were to actually reduce the hidden layers.
Yeah, let me get something to write down, because this is a good idea and I would like to try it. But yes, that makes sense. Yeah, I think there's definitely an overfitting issue here. At least I don't know so much. I don't think there was too much of an overfitting issue with the Romance set yet. That wasn't too terrible. But here with the Uto-Aztecan, it's definitely happening, because the accuracy for training data, it goes up way quickly, and then validation is just terrible. So we're definitely overfitting there.
Yeah, and what I found myself was you showed us the graph of that was your accuracy, if I'm not mistaken, but
The
that
score,
was what I found myself was that when I looked at epoch accuracy for the training set and the validation set, there's a point at which the validation set peters out, but the training set, it absolutely explodes or does something very strange.
Yeah.
And that's when I was able to say, okay, at that point it's really starting to overfit.
Yeah.
So it might be worth looking at both of them at the same time and finding that point.
Thank you. Mm-hmm.
Yeah. I don't know if those, if you wanted to come in on the finite state transducers.
Yes, I had trouble finding my mute button. Yeah, I mean, it's not that, yeah, it's, and I'm actually delighted that someone is really into, well, you're into neural machine translation and would really have to read up on finite state machines, because for me, it's the opposite, I have very little experience with NMT, but a lot of experience with finite state transducers. I mean, the thing with rule-based morphology is you have to know the language quite well, obviously, to design the rules. I mean, you can obviously have a lot of knowledge on it, but if you have never seen the language you're working with, then. But yeah, as Adrian said, if the language is fairly standard, if the orthography and the orthography is fairly standard, and I suppose if it's well, if forms are well attested, if you have a lot of gaps in paradigms and you don't know what the form are, then obviously that's difficult. But if you have a good idea of most of the paradigms, if the forms are standardized, if if you have a lot of suppletion, or I'd say morphophonological tricky bits, then obviously your finite state approach gets harder. But if it's fairly kind of concatenative, even if it's highly polysynthetic, then it works. I worked on Old Irish, for example, which is not standardized. It's poor, it's relatively poorly attested. Not as well attested as many other historical languages, I suppose. And there's a lot of, you have a lot of people work with underlying and surface forms, where the surface forms are very different from the underlying stuff. All these factors combined together make it very hard to actually build a finite state transducer, even though I spent 5 years on that for my PhD. I'm not convinced it's the best way. But if you have a reasonably transparent morphology and a good idea of how the language works, and you have a grammar book, very fairly comprehensive grammar book, go for it, I suppose. And I suppose I can point you to resources and stuff, but I don't know the language, so I can't I would have to study the language, I suppose. Do you speak those languages, or do you have certain commands in those?
Yeah, so here's a problem that will show up, is I don't speak those languages, and for this research I've been flying on my own. I've been trying to get somebody on board who at least speaks some of these languages, but they haven't gotten back to me. so that's kind of an issue. I think for a lot of these languages, fortunately, we do have grammars and smaller lexica, even if the grammars are quite old. However, there's a lot of issues here with basically, with a lot of these languages, you won't really have a lot of experts. And then if it's a real revitalization project, that maybe might be a situation where you can find all of those people in the same place, and get them together and maybe get something like the transducer to work. So another reason also why I went with the NMT approach also was because it didn't require me to actually know the language, right? It only required me to have the data. But if you can find a good, if you can find a revitalization project going on, something like the Opata project, then you could potentially get that going, but that would be quite a long process, unfortunately. But it's a good idea. I think I might look into it. Yeah.
Yeah, I also wonder if you need, for data augmentation processes, if you need to have to cover the whole grammar, or just, just
Yeah.
that raises the whole quality, the whole performance, or just a little bit. I don't know. It seems that these hybrid approaches are very popular these days, but yeah, it really depends on what's available for the language.
Yeah, I mean, that's the general problem we have here, right? There are low resource languages. It's kind of where the problem is buried. Yeah.
Another thing that I was thinking, but again, I suppose, how linguistically informed is the cognate kind of? I mean, does it know that a T is doubled in another language? If you have a line string, I mean, I've been looking at some kind of alignment.
Yeah, the alignment thing is something.
If you align it first, which characters map to each other, rather than just some sequential kind of,
Yeah, that's an idea.
I don't know.
I just thought about very recently, that I haven't implemented yet, but that I think might get a little bit of a better performance, is by fixing essentially the length of each cognate line, or the input cognate. Basically, you take the longest, by character longest cognate in the input line, and then you add sort of dummy characters in the others before you merge them, in order for the model to always have a stable. So basically, the first four are the first four letters, and the second four are the second four letters, because otherwise, since there's gaps in the pattern, by concatenating it, you'll always have essentially you'll have an input line that's made out of 3 cognates, and then you have an input line that's made out of 2 cognates, right? And if there's no cognate in that one language row, then there's just nothing there. So that might also be not optimal. So that's something I'm going to try and run again, is to insert dummy characters to have essentially a sort of semi-fixed length, if that makes sense.
But how do you know where to insert them to kind of keep? I'm thinking
you would just append them at the end, right? Which is still not what you're thinking of, because you wouldn't be able to like align it perfectly, but it would still be better than what it's doing right now, where if you don't have a form there, it's just not present, and then there's no way for the model to know whether it's looking at 4 forms or it's looking at only 1.
So maybe if someone else comes in, a couple people raise their hands, Sino, or
yes.
One major limitation that I see in this work is that the prediction that you would have regarding a cognate in another language or sister language is basically based on the given a list of words that you have. So your model has no way to predict something which has not been observed before in your training process. And that's a huge problem, I assume, because in many cases you don't have enough information or enough data for some languages. Like let's talk about Anatolian languages, which are all dead, and we find an inscription. Somebody comes up with a list of words, and we basically have no way to train any data for it. And then I assume that's the major limitation of your work. But one idea would be, instead of training a model based on your to predict based on the given and observable instances, would be to train a model to construct or generate cognates based on the processes that words undergo. Like, let's say the case of the languages like centum and satum, and how some phonemes change in some language families. I assume embedding that information into your model would be more beneficial to maybe generate cognates and later leave the linguists. I assume you have a lot of problems with linguists believing in your models and that it makes sense, because linguists are so, they would like to have to prove it, and it's a different mindset. But I assume it provides at the end, as the output of your system, a list of the generated words which can be used by linguists, maybe, which can be considered. And there's one example that I think you would be very interested in. It was in 2019 in Brittany, in France. They found an inscription by the sea, which was left, and nobody could decipher it. Nobody could understand what it was about. I found the link. I copy pasted here. You may find it interesting because at the time they were a prize to decipher this inscription, and they were like 1,000 euro, I think. They said for who can decipher the inscription. And I assume the approach and the field that you're working on would be very beneficial to work in deciphering these type of things also by training models on available languages. And those are a couple of ideas, I hope.
Mm-hmm. So in terms of augmenting the model with sort of knowledge about how cognates develop, or sort of I think what you're pointing towards is sort of the historical phonological development, right? I can't really think of a good way to put that into the model itself. Really, the point of having it be a neural machine translation model is that you assume that simply by feeding it the data, the model will learn an approximation of those processes by itself, right? But I don't know if a good way to bake those in. I'm not sure if there are any. There might be, but at least with neural nets, I'm not sure if there's a good way to bake that in. The whole sort of purpose is you just feed it the data and it learns the generalizations that are in there. Unless I misinterpreted your question.
No, that's exactly what I meant. You can also generate data on your own,
right?
Based on you assume it can be a cognate, and then you train. Even a simple classifier would work.
Okay, I think I understand the question a little bit better now. Okay, this is actually something I think I sort of briefly mentioned very much at the beginning, where I said sort of the lexicon that we have limits the amount of training lines, and then I said unless you sort of invent forms. Mm-hmm. And I thought about that idea, which is, I think that's essentially what you're proposing, sort of invent forms that you would think would be part of the language and then train it on that. Mm-hmm. Yes, well, it's a very tricky proposition for me, because apart from, you would have to know the language quite well, but so if you're really inventing a form for the training purpose, the only way I could see it really be sensible would be if somebody from the language community that knows the language invents the form, because we're all sort of in the hypothetical space of a revitalization project, right? And the language belongs to the community. The model only really gives a suggestion. So if you already have a community member or a community linguist inventing forms for you to train your model, then they can just go ahead and invent the form to put into the language, right? Then you've defeated your own purpose. At least that would be my perspective on it. And I wouldn't really be comfortable inventing forms myself for languages that I, am not associated with. Yeah, I think that would be my take here. But yeah, thank you.
Yeah, perhaps to come in here, I mean, one thing we've been looking at that's quite interesting is kind of multitask learning and meta learning approaches, because, and I think Sina was alluding to this, you could sort of learn a model, on language families you have lots of data on, and this could understand things about what kinds of phonetic changes are likely to occur in general.
Mm.
And then this means that by having a model that is already sort of pre-trained, even though it's not in family, might then actually work better on Uto-Aztecan as just because it understands more about phonology. So
I see, yeah.
Doing some similar experiments, different tasks, and I mean, it's something that does seem to work. So it would be certainly an interesting thing to try. And
I see, yeah, okay, yeah, that makes sense. So using some type of pre-trained model, that could be a good way. And I know of people who use similar approaches for just general neural machine translation with low resource languages, where they just use pre-trained models, and that allows them sort of pre-trained models that are pre-trained on just other languages, but it allows them to get away with fewer training data, basically. Because the model has already learned certain types of generalizations that are presumably somewhat either universal or sort of family internal, right? So that would be an interesting approach as well. I saw a raised hand very much earlier from Francisco. I just don't want anybody to.
Yeah. Well, hi. No, John asked me. But I just wanted to know how proficient you were in Uto-Aztecan. So, but I later, now I know.
Yeah, not at all.
Because, well, I think it helps, Yeah. But probably also, I don't know if it's to get informants probably could be an option to just create a little front end, and to get so that people can actually help you. But I don't have that much experience, so I cannot talk to you about models or which way you could improve it. But yeah.
No, the speaker idea is definitely something I want to do, and there are some people at our department who speak or are very familiar with at least one or two of these languages, and I'm hoping to get at least one of them on board. But all of this is still very young, so I'm hoping that the proof of concept will manage to get me somebody who wants to collaborate, who knows these languages as well.
Okay, well, I think Gustav wanted to ask a question in the chat.
Yeah. Hi, Remo. Yeah, this is a very good presentation, and it's good that you are working in these low resource languages. So I have a doubt or question. Like, can you go to the slide where you have said that there is some kind of information flowing on more language addition rather than the data point addition?
Sorry, could you repeat that?
Yeah, you have said in your slide that if you add more languages than the data points, it is working, right?
Oh, right. So I see. Wait, are we talking about this?
Yeah, the Spanish only and the languages if you are adding some languages.
Yeah.
So I have a small doubt or question, like I'm failing to understand why this is happening here. Because does this language or do these languages have the same character representations or the is there any same scripting that is happening, or the sentence constructions are same?
So I use the orthographic representation, right? And all of these languages use a Latin alphabet with various different diacritics, basically. So essentially, I use the vocabulary for the input that just has all characters that occur essentially in the training input, if that's what you're asking.
Yeah. So basically, if I go in that direction, if I think this is a language biasness, and if the languages or the orthographic representation of different languages are very different, like the way they are writing, the word representation are very different, how the model is actually performing better when you are adding more languages, if the representation of the characters are different?
Okay. I'm not 100% sure if I'm parsing the question. But
I will give an example. Suppose you are working with Arabic and Urdu. In both the cases, the way of writing is same. Or if you are working with German and English.
Right. Okay.
So you are in those cases, the writings or the sentences or the construction of words in case of characters are kind of same in most of the cases.
Yes.
So when you add those languages, if you add Arabic for the Urdu, it actually performs better because model is actually understanding based on the character representations. But as you said, in these languages, the way of writing is different, right?
Yeah, but as very marginally. It's all Latin alphabet. I mean, there's some diacritics which, but okay, fair enough. Yeah, they're a little bit different. Yeah.
Yeah, so that's what I'm failing to understand why this is happening, because if you are taking a encoder decoder sequence to sequence encoder decoder on character sequences, and you are taking, at the end of the day, you are taking the representation of the character n-grams. Basically, you are taking the character n-grams. How your model is actually understanding better when you are adding more languages than the data points?
Right. I'm not sure either. Why it does it? So let's go to so what I think is going on is essentially that, well, that's at least my hypothesis here, right? The working hypothesis, but I'm also sort of new to a lot of this, is that having 4 of these forms for some reason helps the model to better understand the target than just having one. I don't know. So you're worried about the character representation, right? Would it help you if the same would happen in, say, IPA? Because it does.
Yeah, but in that case, if you see the example in the second row, in French, it's M-O something in you, because I don't speak French, and then T, and in Portuguese, it is M-O-S-T-O, right?
Yeah.
So if I am learning some model on Portuguese, and if I am adding here French, that will actually confuse the model, right?
Okay, I see. We have a slight confusion here. I'm not training them singularly. The input is this type of Frankenstein input. So it always gets a compression, sort of, it gets a merger of all the available forms. So you're not training it from French to Italian, and then you're feeding it some Spanish, and then you're feeding it some Portuguese. You're always feeding it all the available forms that you have at the same time. And you're sort of trying, or the idea is that via that avenue, you're creating sort of a super representation of the form within the family. I guess that would be the esoteric explanation, right? But you're not feeding it aye, ala, al, and aye. You're feeding it all those at the same time.
Okay, so you are actually putting noisy informations as an input.
Yes.
Okay,
Exactly.
now I get it. Yeah. Okay, now I get it. Thanks. Yeah.
Thank you. No problem. And by the way, I didn't use IPA for this data set, but the Maloney et al. Paper, which I referenced, they did. And sort of the same thing happens, although they don't compare fewer inputs like I do. They just have like one model, basically. But they also get really good performance out of the IPA set. Although in their case, the IPA set performs slightly worse than the orthographic set. And I think that's just because for the Romance languages, the orthography is just more conservative and it retains more of the historical information, whereas the IPA is actually, represents the current spoken form, which is not as frozen as the orthographic form. But yeah, for this one, I used orthographic forms for two reasons, really. First of all, it's more convenient. And second of all, for most of the low resource contexts where I would like to apply this, you don't have an IPA data set available, and they're going to be hard to just produce, right?
I got it. Yeah. Thank you. Yeah. Thanks.
Can I jump in again?
Go ahead. Yeah.
I saw as you were talking to Kustava there, I noticed something about your input data that I wanted to ask you about. Could you go back to the slide where you have the Romance language in, data?
This one?
Yes, this one. So your target in the first case is empty, right?
Yeah, that line would not be in the set.
Oh, okay,
that's
right.
removed.
That was more or less the question.
Yeah, that was kind of the slide. I just wanted to show which types of lines I would remove from the set. So in the actual set that the model would run, line 1 and line 3 would not be present because in one you don't have a target and in the other you don't have an input.
Yeah, that makes a lot more sense than what I was thinking was happening for a second.
Yeah.
The other thing is, even looking at the examples you gave there, you said during the course of the presentation that you thought the reason that taking Romanian out was negligible was because it was so different from the other Romance languages.
Yes and no, if I just may interject. Sure. It was more that it's the smallest, it has the fewest amounts of form in the data set.
Okay, yeah, that would make a lot more sense. I thought you'd said something about it being linguistically different, and I would always have thought French would have been the example there, but clearly, we know that adding even quite different languages, as long as there's enough data, can improve models typically. So linguistically being slightly more different shouldn't make that much of a difference, but having less data would make a lot of difference.
Right. Yeah, no, that was a slight misunderstanding. What I was trying to say was Romanian has the fewest forms, and that sort of goes in line with the historical linguistic view that Romanian is sort of linguistically more distant from Italian, which doesn't necessarily mean that it's more different. It just means essentially it has fewer cognates, because historical linguists used to measure linguistic distance by sort of how similar and how many cognates you have and how similar they are. So essentially saying it's linguistically more distant is just another way of saying it has fewer cognates, at least in the historical linguistic framework, I guess.
I would suggest that maybe there's just fewer identified or recorded instances, because it seems unlikely to me that they just dropped out of existence in Romanian. I know it's geographically quite far away, but Parisian French is very, very different linguistically, I think, at least orthographically. The one last thing that occurred to me, and I know I keep making you jump through your slides, was you, can you just go back through them for a second?
Because
no, it wasn't back quite that far.
Okay. And this is then the Uto-Aztecan. Was this on Romance or Uto-Aztecan, the thing you're thinking about?
I think it was probably the one we were already on with the.
Okay. Sorry. It's, these are. Yeah, this one.
Yeah, this one. No, sorry, it was the one where you were showing us the input.
This one.
This one, yes, exactly.
Yeah.
So one suggestion I might give here, because we were doing a task with cognates ourselves almost a year ago. We started working on it, and I was using a similar LSTM approach. What I found improved the model is I don't know to what level of depth you're going when you're encoding the data, but what I found was when you're putting in data that's kind of concatenated like that, it might be useful to identify which part of it is which language. So there's always something regular for the Latin part,
yes.
sorry, the Spanish part. There's always something, and it could just be, you know, you could put it in if you're doing one hot encoding. There could just be a single number that says, okay, this from here on is Spanish, from here on is French, because what you're doing there is getting the model to guess, okay, from this point to this point, you know, these 3 letters or these 5 letters are Spanish and these next 2 are French or whatever. That's probably very difficult. I think Kostova was getting at that when he said it was noisy, but you could overcome that by having a common character interspersed in there, perhaps, that would identify which part is which.
Yeah, that's something I've been doing with the Uto-Aztecan data, because for this first trial run, I didn't do this interweaving concatenation. Instead, I did a simple word-by-word concatenation, and they're separated with a unique dummy character that doesn't occur anywhere else in the data, to tease them apart. But they're not. It's not like you suggested, like done properly in the encoding. It's just done in the input data. So that's sort of the stupid way of doing what you're suggesting, I think.
Well, I mean, if it works, it's not stupid. What I would suggest, though, is having a separate dummy character for each language, and see if that makes a difference.
Yeah.
All right, thanks very much.
Thank you.
Yeah, so I mean, I have one last question, which probably should be the last one, as we're getting close to half past. So I mean, you discarded the Latin data very quickly, but I kind of wonder, I mean, did you look into how well it would work for Latin? Is it easier to predict cognates from a parent language rather than from sibling languages?
Yeah, that's a very good question, and I was actually thinking about that today as well while I was preparing these slides. I didn't test for the Latin, and the reason I initially removed it was because I thought, well, okay, if this is supposed to be a proof of concept for like a revitalization effort, then we're not going to have the protoforms. So let's not even try and use them. But now that I'm thinking about it, it might have been a bit of a misjudgment, because a lot of the times we might actually have quite a few protoforms, because that's what a lot of sort of earlier linguists were really interested in, right, was protoforms. So we probably, for some of these languages, have quite a few reconstructed protoforms, but then again, they're going to be reconstructed, which means there's always a margin of error. So, but perhaps it might be useful. I'm thinking about running all of the Roman stuff again and some different variations, just to double check some stuff. So I might throw that in there. It's a good idea.
Yeah, and I mean, taking an example would be interesting is we're looking at Indian languages, a lot of very small Indian languages where we don't have much data. And of course, there we have, you know, proto languages like Sanskrit that are very well documented with lots of attested forms. So it would be interesting if we're trying to apply this in, you know, in Indo-Aryan languages, if we can use Sanskrit, and that can be effective here.
Yeah, with these these families that have been the focus of historical linguists very early on, and where we have a lot of these attested forms, I think there it would be a really good idea. With the languages of the Americas, unfortunately, they weren't really that much a focus of sort of the historical linguists of the 19th century. Most of them were documented by missionaries who had, you know, a little bit of a penchant for linguistics. So a lot of the documentation we have for those languages is, you know, Bible translations or grammars that were written by missionaries. And I don't know how much there is in terms of historical reconstruction, but it's definitely an avenue to look at.
Okay, thanks. Okay, that's very interesting. So yeah, so I'll just like to say, yeah, thank you, Remo. It's been a very interesting talk and had a lot of very interesting discussion. And hopefully we can continue to collaborate. Yeah, you know, I think there's a lot of overlap with what we're doing in the project with the kind of research you're doing. So thank you very much.
Yeah, thank you for inviting me. It was a pleasure and very interesting comments and questions. Thank you.
Okay, great. Yeah, so just because we'll have another seminar next week, so that I say next month. This will be at the end of July, and I believe it's me talking. So I'm going to present the Cardamom project and the work we've done so far. That's right, isn't it, Priya?
All right, yeah, that sounds great. Perhaps if someone can send me a reminder of that at some point, I'll definitely be happy to attend.
We'll be sure to send you the.
Thank you.
Once I've written the abstract and the talk outline. Okay, great. So thank you all and have a nice evening and
thanks
thank you all for coming.